So let's talk about a couple things and then we will get started on this set of notes. First off, you have a test a week from today, yeah? And you're going to have a quiz next time I see you. And the quiz next time I see you will be over vessels and blood, okay? Now what you need to know is that your test on a week from today covers just cranial nerves off of that last set of notes, just because we didn't test on them. I wanted you to have more time. And not a ton of cranial nerve questions, maybe 2 or 3, right? Not a ton. Cranial nerves, and then that entire set of notes that included the spinal cord, spinal nerves, and autonomic nervous system, right? And then heart and vessels, blood. So it's 4 sets of notes, okay? Plus cranial nerves. Now, the reason I did that is I could put blood on the 4th test, but the end of the semester is so chaotic that I think you guys would do better having it now than at the end of the semester when you're also competing with lab practicals, right? So the last week of the semester, you have both a lab practical and a lecture test. And then the next week you have a lecture final unless you're making an A. So I think getting blood on this test is actually better for your planning, even though it's a little more stressful, but blood's not hard anyway. It's not a particularly hard set of notes. It's not really like a ton to understand. It's just like, yep, that's what that's called. That's what that's called. Does that make sense to you guys? Okay. So I'm not trying to screw you over. I know it probably feels like a lot, but it is better now than later. Okay. So the 4th test will be lymphatic, urinary, reproductive. Okay. That makes sense? And we will start on lymphatic on Thursday. So, okay, any questions? Oh, the other thing is, you guys on Friday will be starting digestive and respiratory in lab. I don't do those in lecture. They don't do lymphatic in lab. So this is a decent time for you guys to have like a lecture test, right? Because it's not lecture and lab are not overlapping. Why do we do that? Because sometimes we need to cover some body systems lightly so that you've been exposed to them. So they'll choose to cover them in one versus the other. Usually the ones that I know are really difficult, I make sure we cover them in both so that I can help you through them. But digestive is like freaking tube. Different parts of the tube have different names. How the hell hard could it be, really? You're like, this part's called that, and that part's called that. I'm like, okay, you're done. Digestive and respiratory, and then we're going to do lymphatic mostly because people have never been exposed to lymphatic before, and it's part of the immune system, and you might want to know about it. Okay, so let's talk about blood today. Blood, the reason I want to do this is just because it helps you with phys. And also because it's kind of an interesting immune system story because the blood's involved in the immune system as well. So just before we get into the nitty-gritty of it, I know you guys have heard that people use the term cardiovascular and circulatory. FYI, what's the difference? Circulatory is everything that circulates, so it includes the lymphatic system. Cardiovascular is just heart and vessels. Okay, I don't nitpick you about that, but this, when we get to the lymphatic system, they start using them differently. So you guys already know this, but the basic pattern, with a few exceptions, of blood circulation is heart, arteries, arterioles, capillaries, venules, veins, heart, right? And the exceptions to that are, of course, like portal circulation, but we're not particularly concerned about that today. So let's talk about what blood is made of. We'll do the boring parts first, and we'll start talking about red blood cells, and we'll start talking about immune function. So believe it or not, blood is, of course, a connective tissue. Does anybody remember what makes it a connective tissue? Because I acknowledge that it certainly doesn't seem like one. What is it that makes it categorized as a connective tissue? Do you remember?
It comes from the same stem cells.
Yes, exactly. Because in mesenchyme, right? It's derived from mesenchyme. So it's actually considered a fluid connective tissue. It's got living cells, which are called formed elements, in about 92% water matrix. So the matrix is mostly water. As far as the quantities of blood that you have, typically males have between 5 and 6 gallons and females have between 5 and 6 liters, which is a gallon and a half. And females have between 4 and 5 liters. Now, that doesn't mean that there aren't women with more blood than men. It just is accounting for the difference in body size, generally speaking. Male blood is, by the way, slightly different than female blood, and we'll get to that a little bit later. It has greater oxygen carrying capacity because of testosterone. Okay, so if you take a blood sample and you centrifuge it. You guys know what a centrifuge is? It's like a really fast test tube merry-go-round, right? Stick them in at angles, make sure you balance them. One time in graduate school, I forgot to balance it. And one of the test tubes, in addition to making the most horrible sound ever, ended up being embedded in the ceiling. I ran out of the room, pretended like I had no idea who would make such a horrible mistake. I totally did too, and I never told the truth either. So what do you do? I was like, I just started graduate school. I'm definitely getting kicked out. So what you do is you spin them down, and of course the denser stuff goes to the bottom. Why do you think that red blood cells are the densest of dense things in here? Yeah, full of hemoglobin, which has what in it? It's really heavy. Iron, exactly. So red blood cells are the densest, and they go to the bottom. Then the white blood cells are the platelets, and then the fluids, right? So when you look at this, you can see what's called a hematocrit. And the hematocrit is when you spin your blood down, the percentage that is solids versus the percentage that is liquids. So this is considered the hematocrit. 1% is always just for white blood cells and platelets. It's mostly red blood cells. So we'll talk about hematocrits and differences between males and females. So when you centrifuge a blood sample, the bottom is red blood cells, usually 44-ish%. It varies, and it varies in males and females, and it varies depending on your health. And this is usually 1%, white blood cells and platelets, and this is blood plasma is usually 55%. Now, why would you do this? Why would you do a hematocrit? It's a really good way to get just an eyeball on what's going on. For instance, if you're super dehydrated, right, your blood plasma is going to be a disproportionately low percentage, right? What if I am anemic? Then my red blood cells can be very low. What if I have an immune reaction to something? Then my Buffy coat can be way thicker, right? What if I have leukemia? Then my Buffy coat's enormous, right? So it's like just really like a quick eyeball look at what's going on with the proportions of your bloods. It's generally not the final test that is done. It is usually one of the first tests that's done. And it's also pretty damn cheap compared to most things. I mean, you don't even have to count it. You just spin it down, you like estimate based on the look, right? A CBC is more expensive because you have to like count all of the blood cells on a slide. So this is a hematocrit. So what do you see for hematocrits in males versus females? Males have between 42 and 52% solids in their blood. Most of that is red blood cells. Females have between 37 and 47%. Now, why the difference? And the difference is that testosterone and other androgens cause erythropoiesis, which is the production of red blood cells. So males have, per same volume of blood, greater oxygen carrying capacity because of testosterone. This is post-pubertal males, when after they go through puberty. That makes sense? So slightly more blood, generally speaking, and then greater oxygen carrying capacity in the bloodstream as well. Okay, so we'll talk about how you get to the low end versus the high end a little bit later. Okay, and then the fluid, the blood plasma, that percentage that you have averages 55%, but it's pretty variable. It's from 46 to 63, depending on how hydrated, dehydrated, how many solids you have in your bloodstream, and all that kind of stuff. So what I want to look at first is do the boring part. Let's look at the blood plasma and what's in there. It doesn't make for a good story, and there's no good pictures because it looks like yellow fluid. What is in the yellow fluid? Mostly water. See, it's not a very exciting story to tell. But then in addition to the water, there's also, it is mostly water, which means it's a great place to carry water-soluble stuff, like ions and proteins, right? Okay. Some of your gases travel in there, some other things travel in there. And then there's a whole bunch of proteins that are traveling in there. Like your hormones travel in there too, by the way. That's why they're considered regulatory proteins. And then you've got albumins and globulins and fibrinogen. So I just want to talk about that. Albumins is by far the most abundant protein that you have in there. And the function of albumin is it's a really small and really abundant plasma protein. And what it's primarily for, although not exclusively, is that carrying lipid-soluble stuff around in the bloodstream is problematic because lipid-soluble substances are like toddlers with ADD. Like if I'm trying to get it to go from this end to that end, right? But it's lipid-soluble. It just like sees shiny objects and like diffuses out over there and over there and over there. So what happens is the liver makes albumin, and albumin holds on to lipid-soluble substances to get it from point A to point B, and then it lets it go at point B. Does that make sense? Okay. So that's a really important function for albumin. The other important function is sort of secondary, but it is pretty damn important. Because albumin is staying in the blood plasma. Remember I told you when we go through a capillary bed, the arterial end is high pressure, so we tend to lose a lot of fluid, right? And then I told you at the venous end, we pull most of it back by osmosis, so lose it by filtration, pull it back up by osmosis. This is one of the huge osmotic draws because there's so much albumin in there, right? So it actually is helping you to maintain your blood volume by doing that osmotic draw. Does that make sense? Okay, and then I have globulins. And globulins, they actually literally named because IN means it's a peptide or a protein, and it was glob-shaped. So somebody's 4-year-old got to name it a globulin, okay? So the globulins, you have alpha and beta globulins, and those are antibodies made by your white blood cells. And then you've got gamma globulin. And gamma globulin, I have better experience in Utah with people having heard of gamma globulin than in Texas because there's a big military presence here, and in addition, there's a lot of people who went on foreign missions here. So a gamma globulin shot, oh sorry, I said that the alpha and beta were antibodies. Gamma globulin are antibodies. So these would be made by your white blood cells, and they would be made in response to exposure to a specific pathogen. Okay, so antibodies are little proteins that you make when I get exposed to, for instance, chickenpox. Then I make antibodies that are specific to chickenpox and won't attack anything else. So I know that I have antibodies for chickenpox and strep throat and a bunch of things that I'm going to encounter in North America, right? But I probably don't have any antibodies for dengue fever or malaria, right? I've just like never been to like Central Africa. I've never been to a lot of parts of the world in which I would get exposed to those things. So let's just say that I was going on a trip, right? And I knew I was going to go to areas of the world that I did not have antibodies for common pathogens there. Well, now what they've done is they can make up antibodies in the lab for pathogens that you are going to encounter or likely going to encounter in different parts of the world. So if I were going to sub-Saharan Africa, they would give me antibodies that are specific to those pathogens there. So they give you a gamma globulin shot. Has anybody had one in here? No? Yeah? It hurt, huh? They call them peanut butter shots because they're like so thick and viscous. And they make your tissue really sore. I've heard for like about a week afterward. So what's the point there? The point there is just to give you an immune system buffer so that the first time you get exposed, you don't get ill, right? It doesn't last for a very long time because you actually metabolize those antibodies. But during the process of metabolizing those antibodies, you're also making your own antibodies, right? You could do it naturally. You could just get freaking sick as hell when you first get exposed to everything, right? But this will actually give you a little buffer system. Does that make sense? So interestingly, because we are more of a global population, gamma globulin shots are slightly less common than they used to be because like we're carrying pathogens all over the place. But there are still some pathogens that are just like really localized populations. So the other ones, these two, alpha and beta, are similar to albumin in their function. They're used for carrying things around that have trouble getting from point A to point B, like lipids and some iron and copper and some vitamins. And then the other thing that's the most abundant proteins, you've got albumins, globulins, and then you've got clotting proteins, including fibrinogen. And you go into a lot of detail about fibrinogen in Phys. It's a clotting protein. Okay, so other stuff is carried in the blood plasma, anything water soluble. Enzymes, hormones, waste products, nutrients, some gases. Most of your oxygen is carried inside your red blood cells, but you always have a little bit in your blood plasma. And electrolytes, which is just a fancy word for ions. Electrolytes like sodium, potassium, calcium, magnesium, all those kinds of things. Okay, so now let's get to the more interesting part, which is just the cells that are actually in there. So they actually don't call them cells, interestingly. And the reason they don't call them cells is because platelets are actually cell fragments. So if you want to talk about all of the solids in blood as a whole, they usually call them the formed elements instead of blood cells, because only these 5 are cells. Well, sorry, 1, 2, 3, 4, 5, 6. So the erythrocytes are cells as well. Platelets are not whole cells. Okay, so let's talk about where you get your blood and the process of blood production. First off, the process of blood production. I do not hold you responsible for this in detail, but I do hold you responsible for it generally. Okay, the process of blood production is called hemopoiesis. Okay, and it occurs where in your body? Red bone marrow, exactly, in an adult. Okay, so look at the beginning and then look at the end. So this process of blood cell production starts with a cell that's called the hematocytoblast, which should make sense to you, or hemocytoblast. Nobody can ever decide whether to use hemato or hemo, and it doesn't make any difference because some textbooks use one and some textbooks use the other. So a hemocytoblast, which literally means blood cell precursor, right? And from that, you get two stem cell types. This one's called a lymphoid stem cell. This one is easy to remember because it only makes lymphocytes. And then the myeloid stem cell makes everything else, including all of the rest of the white blood cells, plus red blood cells and platelets. And we'll come back to this in just a second. Okay, so the entire process is called hemopoiesis or hematopoiesis. So where does it come from before you have bone marrow? Right? So it's weird to think about. Isn't your baby almost due? When's your baby due? Today. Oh my God! What are you doing there? Go away! Oh my God!
She's furious.
Oh, she is.
Yeah.
Tell her I'm sorry.
Yeah. Like we went to the.
Well, you got your phone on you, don't you?
Oh yeah.
Okay.
She's here.
If it rings, he gets a pass today, right?
Oh, of course he does. We didn't have a quiz.
I was like, just in case, but she's furious. We went to an appointment together because we were going to talk about whether or not she get induced or not. And I said what I thought, which was like, he'll come when he comes. And she looked at me and I was like, okay, this is where you say what you want. She didn't say anything. She wanted to be induced, but she's not saying what she did.
Oh, she's not being induced.
She's mad at me for saying what I thought. She told me to come and say what I thought.
Nobody really means that during the
Yeah.
pregnancy
Like,
process.
come and say what I want you to say.
Come and say what I think, and say it twice, right? So, embryonic origins of blood. Where does the blood come from before the baby has red bone marrow? So, after about week 3, which is like 4 weeks after you had sex, 3 weeks post-implantation, right? Because it takes a week for implantation to occur. You actually have a yolk sac during a lot of the development of the baby. I know that's weird to think about, but you have a yolk sac just like a chicken had a yolk sac. And before you have any parts that are at all recognizable as human parts, or even animal parts, you have a yolk sac, and the yolk sac will start at about week 3 to make blood cells for the baby and dump them into the bloodstream. It's still just basically an embryo at this point. Maybe somewhere between an embryo and a fetus. It doesn't look anything like a critter yet. But then at 2 months to 5 months, then your liver and your spleen, those soft tissues are starting to have limited functionality, and then they will take over red blood cell production. Interestingly, your liver and spleen still remember how to do red blood cell production. So if you ever hemorrhage, but you're otherwise healthy, when you are replenishing your red blood cells, not only is your red bone marrow working its little butt off, but so is your liver and your spleen. They will try to help with replenishing. So your liver and your spleen do it from 2 to 5 months, and then after 5th month, you have red bone marrow, and now your red bone marrow can actually do it, okay? So in children, remember when an infant is born, there's red bone marrow pretty much everywhere, and then it slowly diminishes until adulthood, and it's left behind a few places, you know, your sternum, your os coxae, the heads of your humerus and your femur, and those kinds of things. Does that make sense? Okay, so the kinds of cells that do it, as I mentioned, were hemocytoblasts or hematocytoblasts. And then one more time, let's look at this. The hemocytoblasts will almost immediately differentiate into these lymphoid stem cells or these myeloid stem cells. Have you guys ever heard of myeloid leukemia or lymphoid leukemia? Okay, if you have, then you can kind of start to understand symptoms of either one. If you have myeloid leukemia, you are going to have a problem with red blood cells, platelets, and 4 of the 5 types of white blood cells. It's a big kind of leukemia, and it makes non-functional but abundant of all of these, and they sort of crowd out the bloodstream. And then with lymphoid leukemia, because of the special functionality of your lymphocytes, they kind of like take out the generals of the immune system, and we'll talk about the function of lymphocytes a little bit later. Okay, go ahead.
Have you seen that video? Jeff was showing us a video of lung tissue making platelets.
They just learned that, like last week, it was just published that the lung tissue actually has blood cell and platelet production functionality.
Super cool.
Yeah, I haven't read the article yet. I did see the video, but I want to read the literature article. What? Just what? I'm super confused by that, but I'm glad. It's good. It's nice to be confused, right? It keeps you humble. Okay, so now let's talk about erythrocytes. So there are your erythrocytes right here. And you talk about this in quite a bit of detail in physiology, but I want you to look at overview the process of production of red blood cells. That process is called erythropoiesis. The whole process of blood cell production is called hemopoiesis. That's more general. Erythropoiesis is more specific. Now, you have boatloads of red blood cells. All of this starts in your red bone marrow, and the cells that are produced have a very unique shape and a relatively unique function. So let's look at the unique shape of a red blood cell. You guys have seen this many times before. The shape is a biconcave disc. They're incredibly regular in both their width and their height, and that's really important because the smallest capillaries, they have to go through almost single file. They have to stack up like Rolos, right? And as a matter of fact, that's where the word Rolo came from. Because the French for stack is rouleau, right? So that's where your Rolos came from. So they have to stack up and go through single file. This shape also gives them some other things. It gives them the ability to bend in the middle if they have to go around an acute angle, right? And also, this shape compared to, for instance, a sphere, which a lot of cells assume, has a higher surface area to volume ratio, right? So you've got really good exchange of oxygen coming in and oxygen going out, which is really their job in life. What it really is, by the time this thing is mature, is a bag of mostly hemoglobin. Because you can see what is actually happening in this process right here. Okay, what's happening is hemoglobin is a protein. We'll talk about it in more detail in just a second. Hemoglobin is what makes your blood red. It is also what carries oxygen around. When oxygen binds to hemoglobin, blood becomes redder, right? So in this cell, what's going to happen is I have to do hemoglobin synthesis before the nucleus is ejected. Because, of course, you need DNA for protein synthesis, right? So what's going to happen with these guys is you can see it getting redder as it does hemoglobin synthesis, right? And then at some point you actually eject the nucleus and almost all of the organelles, which really limits the functionality of a red blood cell for the rest of its life. It certainly limits it to 0 cell division, right? You can't go through cell division without a nucleus. You can do no protein synthesis to speak of. That means that every time I need new red blood cells, I have to go back to the origin, to the red bone marrow, right? Okay, now by the time you're done, this thing is mostly just an empty bag that's filled with hemoglobin. So let's look at hemoglobin briefly. Hemoglobin is basically a peptide or a protein. It's got 4 subunits, 2 alpha, 2 beta. The important thing about it is that the center of each of these chains is what we call a heme group, and it's got like a little flying saucer looking structure in there. That is an iron molecule, or an iron atom with some other stuff around it, and you carry oxygen gas, O2, here, 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 and here. So you can carry 4 molecules of oxygen gas on each hemoglobin molecule, and that means that when oxygen binds to the iron in hemoglobin, it makes blood red, just like when oxygen gets exposed to iron in the environment, it makes things rust, it makes them turn red. Does that make sense? That's sort of the basis of this. So they lose their nucleus. Red blood cells get the crap beat out of them as they're going through those tiny little capillaries, and they don't live an incredibly long time, and you have to go back to the red bone marrow to get them. They live around 120 days. How do they get trashed? They get trashed because, remember, as they go through the liver and the spleen, remember the liver has these sinusoid capillaries, and usually you think of the macrophages as looking for pathogens. They also look for weird-looking cells. And weird-looking red blood cells are pretty damn common, and if it starts to look weird, they just scoop it up, trash it, and recycle the parts. So as it goes through the liver and the spleen, it's always just getting assessed to see if it's got one more round left in it or not, and if it looks really abnormal, they'll take it out. Okay, so during development, you make hemoglobin protein, and it's completely packing this structure. Okay, so I briefly want to go through the basis of blood typing, which most of you guys have done at some point before, but instead of memorizing it, I actually want you to kind of understand it. Okay, so I want to go through the basis of blood typing and why it exists, like why it evolved, and then what's the clinical relevance to blood typing. So there's a bunch of blood typing systems. The ones that I know you've heard of are the ABO system and then the RH system, which is the positive and negative. But there's also 2 or 3 more. One of them is the MN system. They don't usually test for those unless you're doing really specific organ and tissue transplantation, and then they have to have a better match than this. Well, let's go through the ones that you've talked about. So antigens are genetically determined protein and sugar complements that stick up from red blood cells, and other cells too, but we're talking about this specifically with red blood cells. And antigens are genetically determined, and they do not look at all like that. They're like sugar chains, but they're specific. And their functionality, evolutionarily, is to identify self to self. So my white blood cell, which is the vigilant, like gatekeeper and protector of my system, needs to know what kinds of cells to let pass, right? And so what happens is your cells, red blood cells included, will have a flag on that the white blood cell can identify, okay? And whenever it sees something that it recognizes, it says don't trash it, right? And it also has the capacity to recognize foreign things. So if I have A's, I do not attack A's, right? But I attack anything that has not A, right? So I have antibodies, which are these attack proteins. Think of them as heat-seeking missiles for anything. Antibodies are interesting because, of course, antibodies you make for pathogens, we talked about them in the context of gamma globulins. But your body thinks that anything that doesn't have the right flag is a pathogen and should be treated that way, right? So it does the same thing to foreign antigens. So if I have blood type B, I won't attack B's, but I certainly will attack A's, right? If I have blood types A and B, I can't attack A's or B's, right? Because I'll trash myself. If I have blood type O, which I do, okay, I will attack any A or B. So I'm blood type O. Anybody in here AB? It's not very common. No? A or B? No? We don't have any A's or B's? Yes, okay. So if she gave blood to me, what would happen is I would launch a massive immune response. And the worst that could the best that could happen is I would feel like crap, and the worst that could happen is, depending on how much blood she gave me, I could actually die because of the mismatched transfusion. Okay, so when you look at the ABO blood groups, one of these is considered a universal donor because it doesn't have anything to elicit an immune response. Which one? Oh, yeah, I'm the universal donor, sort of. Who's the universal recipient? AB can accept blood from anyone, right? My phys professor called type O the blood slut because you could give it to anyone, and type AB the other blood slut because she'll take it from anyone. It was very politically inappropriate. So let's talk about the RH types, because most people, when they talk about their blood type, are going to give you both the A, B, O complement and also the plus minus complement. So we talked about this briefly last time. The RH blood types are simply, do you have this antigen or do you not have this antigen? If you do, you're positive, and if you don't, you're negative, right? Okay, so I'm actually not the universal donor because I'm O positive, okay? And the universal donor has nothing at all to elicit an immune response, so that would be O negative, okay? Does that make sense? Okay, so this is the RH factor. So who is the truly universal recipient who can pretty much take blood from anyone? AB positive, yeah. So you don't have the capacity to recognize any flag because you have them all, and you can't launch an immune response against any flag. Now, that doesn't mean that, by the way, anybody can take O negative at any time. Sometimes you're so immunocompromised that you actually need a specific match. But if we're talking about just a general blood donation with a person with no immune problems, O negative is generally the universal donor. Go ahead.
So this is kind of a long question, but why is it that we evolved to have these different blood types?
I don't. It's an evolutionary anomaly. We didn't even know that existed for a really long time. So one of the things that happened in 1700s, I don't know if that's true, but is they started figuring out that blood transfusions could save people, but they were really confused because they started doing it in dogs before they did it in people. And they just would give a blood transfusion from a well dog to an ill dog. And it just worked. And it just kept freaking working. And it was fine. It was like, hey, blood transfusions. And then they started doing it in humans, right? And it would either work or kill you dead as a hammer. And they could not figure out why. And it seems as if not very many mammals have blood groups. So these are just antigens that we evolved. Dogs don't have blood groups. Dogs have dog blood. Just period. I don't know about cats, right? Cats have got something funky, you know, something weird going on there. But humans have these, so I don't know. Probably just an evolutionary anomaly that developed because we had like one group of humans that moved out and then existed in multiple different, it's called the founder effect, right? You have humans that exist in multiple different places and then they have times for mutations to develop, right? And then the groups get back together. So that's what I would imagine that blood groups are, because I know that blood groups are different expectations for different groups. Like I'm part Native American and my blood group is more common among Native Americans, and there's more common blood groups in the Middle East, and there's more common blood groups in like parts of Africa. So it's probably what it has to do with, just sort of this genetic, like evolutionary lineage. Okay, but we talked about RH factors last time, right? We talked about babies and RH and ROGAM. Okay, didn't we in here? Yeah, we did. Okay. So there's also an MN system. Like I said, if you are going to do a tissue or organ donation, like the first question is blood type. But then there's about 72 other questions. There's about, last time I checked, and I haven't checked within the last few years, so it's probably different now, there were 20 different antigen-antibody matches that had to be made for tissue or organ donation, not just these, right? So that's why, like, even if I wanted to give somebody a kidney, I can't just give them kidneys, right? They have to actually match. Okay, so there are some disorders of red blood cells. Let's briefly talk about them. So can you have too few red blood cells? Can you have too many? Yes, most of us are Goldilocks and we've got just the right amount, but there are too few and there are too many. There's a million different types of anemia. One of them has to do with too few red blood cells. This is reduced oxygen carrying capacity. This one can be due to too few red blood cells. It could be due to too little hemoglobin, but regardless, does it make sense that the symptoms of anemia would be you're kind of freaking exhausted, right? And you're chilly and you're pale and you don't have enough energy to do almost anything. Anemia is not at all uncommon in women during their reproductive years immediately after they menstruate, right? Immediately after they menstruate, and it can come back. You can protect yourself a little bit from that anemia by making sure that you get plenty of iron and therefore have plenty of hemoglobin before menstruation and then during menstruation as well. But women have a predisposition to anemia that men don't generally have. There's also the other problem. The other problem is too many red blood cells, and that's called polycythemia. And that can be because of like myeloid leukemia, right? If you get myeloid leukemia, you can get way too many red blood cells. But it's also happening over and over again now because we actually know how to make a hormone that causes erythropoiesis. It's this hormone right here called EPO. EPO is produced in you, normally, by the kidney, targets the bone marrow, and it tells you to make more red blood cells. Like, for instance, you would do that immediately after you gave blood. You would make EPO, and you would say, I need more red blood cells. And more red blood cells means greater oxygen carrying capacity, right? So we figured out how to make EPO in the lab, and it's pretty useful clinically. Like if someone had chemotherapy because of leukemia, it's going to trash their bone marrow. And part of the problem with healing from that is that you don't have enough oxygen being carried around for healing. So you can shoot somebody up with EPO and increase their oxygen carrying capacity and they can heal a little better. So that was why, one of the reasons that EPO was developed in the lab. So we can make it in the lab. And now that we can make it in the lab, people have started to abuse it. And they've started to abuse it by using it to get an athletic advantage during competitions, especially at elite levels of athletics. Cycling is famous for use for EPO. But let's talk about the normal relationship of EPO to red blood cell synthesis. So generally speaking, elite athletes, long before blood doping, knew that if you trained at higher elevations, right, you would get the advantage of making more red blood cells. And then regardless of whether you competed in Park City or Louisiana, you'd still get more oxygen carrying capacity, and it's like an advantage. And the reason that occurs is because at lower elevations, there's more oxygen in the air. So I come from Texas, which is pretty close to sea level. Lower elevations, there's more oxygen in the air. So I don't need as many red blood cells, right, when I'm living in Texas, yeah? And then what happened in my story is that I moved to Utah, okay? And I moved to Utah, and I made the mistake of moving to Provo, because I don't know what the hell I was thinking. And they don't like my kind there, and I invited the neighbors over for margaritas, and they never spoke to me again. That is what you do in Texas. That is literally how you make friends, right? I was like, what the hell? And then I said, what the hell? And then they never even let my kids play with them anymore. So that was a problem. But in addition, I also couldn't walk up the damn stairs. I'm like, oh my God, Utah's trying to kill me. Because I have no oxygen carrying capacity for this high elevation. And so what happens is once your body knows that you are going to stay and you're not just going for a day trip, because this is expensive to make more red blood cells. So after I had been here for like 2 weeks, my body was like, you're staying in Utah, Melanie? Have you met you? And I'm like, yes, I'm a missionary to a foreign land. I'm bringing my culture to them. Once I decided I was going to stay, then I made more red blood cells. And then all of a sudden I could walk up the stairs. Unfortunately, when I got to the top, I was still in Provo. It was a problem. And then I moved away after a year. I moved up to Salt Lake. So if athletes use that to their advantage too. No matter where they are going to compete, they train at high elevation, and not just for a few days, but for months, right? Okay, but since everybody started doing that, it's no longer a competitive advantage. So how do you get better than the next guy who is also an elite cyclist, right? Then what you do is you're like, oh, well, let's see if I can get even more red blood cells. And I can take EPO, which is sold for like chemotherapy patients, and I can shoot myself up with it. And the problem is that can cause polycythemia, which means you've got too many red blood cells. Why is that a problem? Too many red blood cells makes your blood so viscous that you can't pump it. So it would be like instead of whole milk, maple syrup. And you can have heart attacks and strokes because of that. So that's called polycythemia. So they shoot themselves up and it increases their red blood cell synthesis. Lance Armstrong said that he did it, right? He didn't need to do that. He was already amazing. He like screwed up his record and made a permanent asterisk in my head for whatever his accomplishments are. He was already amazing before that. But then there's another way to do blood doping, and that is I give my own blood, I stick it in the fridge for a couple of weeks until I regenerate the blood that I gave, right? And then I take my own blood and shoot myself back up with the red blood cell components of it. That's the other form of blood doping. The problem is it's really difficult to detect blood doping because EPO has a really short half-life, right? So you can't really detect it. And those are your cells, right? Regardless of whether you stuffed them back in or made yourself make some more. So what do they do now? The last time I checked, which was last year, they say if you are going to compete in this athletic sport, you can have a maximum of this many red blood cells, and I don't care how you got the rest of them, you are not playing, right? And it's a really generous amount. It's not something that any of us would ever get to, right? Because of course they have been training at high elevation. A lot of them have a decent amount of testosterone, right? And they are really cardiovascular athletes. So if you get above a certain amount, they're like, well, I guess you better sit on the couch at sea level for a little while or else you ain't gonna compete.
So they just take them out?
Yeah, they won't let them compete at all.
Well, I mean, like, so could they just take out the red blood cells?
No, no, they're not allowed to do that either. They test them right before the race, and then if you are above the level, you just can't compete.
So you would be testing like for a month previously to make
Yes.
sure you didn't go over.
To make sure you didn't go over, yes.
So then you could just take some out so you could still compete before?
I don't think they'll let you take them out right before. I think that they assume that that means that you have been cheating in some way, shape, or form.
So you sit on your couch.
Yes, you sit on your
Like, oh,
couch
no, I gotta cut
and
it.
watch everybody else. But there haven't been situations that I know of yet in which somebody who wasn't cheating actually got knocked out of the running because it's like such a generous amount.
Cheating.
Oh, I know, they're all
And it's-
cheating.
I mean, so many sports, I just might as well just say, whatever, guys, do what you need to do.
Yeah, I don't know why we
Like,
care
if
so
everybody's
much.
doing it, is it really an advantage anymore? No. So just be like, hey, do whatever you want.
Or we could just say, how about everybody not do it? What did you say? What did you say?
That goes against everything my mom told me as a kid. Just because the other boys are doing it doesn't mean
They're all doing it.
They are all doing it, and they're all grown-ups. As long as you're a grown-up and you're over 21, I don't really care what you're doing. But I also don't care if you die either. Like, that was dumb. Why'd you do that? It was pretty dumb. Okay, so that's polycythemia and anemia. You've probably heard, I know that a lot of times they teach sickle cell. Have you guys heard of the relationship of sickle? Have you guys learned this before? Sickle cell anemia?
Yeah.
Okay, you have. So I just want to go through it. So I just want you to see like this little evolutionary anomaly that makes this deadly disease still really common. You probably covered it before. I teach in genetics. What?
There's some advantages to it.
There are advantages, exactly. So this is a normal red blood cell, and this is a sickled red blood cell. So what happens is there is a single point mutation. Okay, it's a single amino acid, nucleotide substitution that causes an amino acid substitution. What it does is that amino acid substitution causes hemoglobin to fold differently. And then if you ever get these cells into low oxygen conditions, they will sickle like that. What's the problem with sickled cells? The problem with sickled cells is they can't get through capillaries. They cause a tremendous amount of pain. If the tissue downstream is dependent on oxygen, the tissue's going to die. So they can cause heart attacks, they can cause strokes, and the sickle cell crisis is supposedly outrageously painful. So, and this disease, typically speaking, historically speaking, was way more likely to be deadly before someone reproduced. So a disproportionate amount of these people would die in their childhood or early teens. So a lot of them weren't reproducing. And yet, it is still outrageously common compared to a lot of deadly diseases. 1 in 400 people of Central African descent either has or carries sickle cell disease. Yeah, it's because of the link to malaria, exactly. So let me tell you about the genetics and then we'll link it to malaria. So here's how the genetics works for sickle cell versus normal. I can't use S's because they look the same, big and small, so let me just use A's. So if you have 2 normal alleles, then you are going to have a normal shaped red blood cell. Good? Okay. If you have 2 mutated sickle cell alleles, then whenever you are in low oxygen conditions, your blood cells are going to sickle. Does that make sense? If you are a heterozygote, what happens is your blood cell is mostly normal and hardly ever sickles. Like it would sickle if you were drowning, but it's got like a slight bend to it, just a slight bend to it. It doesn't usually have any pathology associated with it in most situations. So this person would probably not even know that they were a carrier unless something really dramatic happened. So the question is, if this one killed you disproportionately, right? Historically speaking, I'm not talking about every individual. I'm talking about evolutionarily over hundreds of years or thousands of years. Disproportionate amount of those people died of sickle cell. Then why the hell now, in this day and age, do we still have 1 in 400? Well, the answer is, funny enough, that these guys disproportionately died of malaria. And here's why. I'm going to draw a really bad picture of Africa. Ready? It's going to look like a chicken leg. It's Africa. Totally is. The central portion of Africa right here, and also some portions of Asia, are really moist. Moisture, mosquitoes, malaria, right? Okay. So malaria is still a global, huge problem that we're trying to overcome. Malaria is an intracellular parasite inside red blood cells. But the problem here is that malaria only likes these kinds of red blood cells. So can you see what happens over time? Is that disproportionately these guys died of malaria, disproportionately these guys died of sickle cell anemia. So who disproportionately are the survivors? The carriers, right? And so every time 2 carriers get together, what's the chance of them having 1 in 4, right? 1 in 4. They produced 2 carriers, assuming that it was like they had 4 kids and they were exactly the proportions that you imagine. But globally, generally what happened is you would have 1 homozygote dominant who didn't carry it at all, 1 potential affected person, 25%, and then 50% carriers. So you're producing lots of carriers in the next generation and potentially producing people with sickle cell in the next generation. And it just stays in the population. They continue to stay in the population. So it's disproportionately high in people of Central African descent in some portions of Asia. Asian descent. Does that make sense? It's just that weird little evolutionary anomaly, little selective pressure for the heterozygote. Okay, so now let's talk about leukocytes. Leukocytes are actually kind of the interesting part of the story, if you ask me, but they're a little harder to figure out. Okay, so these are white blood cells, and there are 5 different kinds. And to remember the 4 proportions of the 5 different kinds, you remember never let monkeys eat bananas, and those are the 5 in order of how abundant they are. Nevers, neutrophils, let, lymphocytes, monocytes, eosinophils, and basophils. Now that's assuming that you don't have any kind of infection. If you have an infection, then proportions will change, okay? So never let monkeys eat bananas. They, at the best of times, are not very abundant compared to red blood cells. Remember that both the white blood cells and the platelets combined only made up 1% of hematocrit. This would change dramatically if you had some kind of pathogenic infection, but it's still pretty small. They're way larger than red blood cells, and they have nuclei. Part of how you can identify them is by the shape of their nuclei, and I will actually teach you how to do that. So they all have nuclei. They're way larger than red blood cells, but they're way less abundant. In a cubic millimeter, red blood cells, 4 to 6 million red blood cells. In a cubic millimeter of a person without an infection, you have 4 to 11,000 white blood cells. 11,000 is the high end. It probably means that something's going on. 4,000 is the low end. So way less. And the other thing about white blood cells, unlike red blood cells, is that white blood cells don't have to stay in the bloodstream. They can move out. So if you were healthy, your red blood cells are sequestered inside your bloodstream. If you are healthy, your white blood cells should not be. There will always be some in your bloodstream, but some of them move out by this process called diapedesis, kind of like an amoeba moves, right? In which they stick a cytoplasm or stick a foot out and then they flow into it. These guys do this to get out of the bloodstream. This is called diapedesis. And why? Because they live in like connective tissues and help protect you. And then some of them actually move into the lymphatic system as well and live in the lymphatic system. So white blood cells pretty much rove all over the body with the exception of like the central nervous system. They don't really get into there. So that process is called diapedesis. And so your leukocytes do two things, and they're different, and it's important. The difference is important. Leukocytes function in defense, and they also function in immunity. So let's talk about the difference between defense and immunity. Defense is I walk around a corner and somebody cracks me in the face and I hit them back. That's defense. Immunity is remembering that there's a bastard around that corner the next time, right? And exactly what his weak spots are, right? So immunity is your smart, your future-reaching protection, okay? Immunity helps you prepare for further exposures. Defense is just a response to an immediate stimulus, right? And your white blood cells are responsible for both. And one of them, you can actually have the capacity of building. Which one? You build your immunity. Your defense is still real time, right? It still responds real time and it's still important. But your immunity gets stronger, we hope, as you get older. So immunity is preparing the body for the next invasion, and defense is response whenever the invasion occurs. So a white blood cell count of 11,000, above 11,000 really, is called leukocytosis. And it indicates an infection somewhere in the body. And one of the ways that they could gather what kind of infection it was is instead of doing a hematocrit that just says I have a bunch of white blood cells, you could do a CBC, a complete blood count, right? And then instead of saying I have a lot of white blood cells, I can say, oh, I have a lot of basophils. And that can tell me X, right? Or I have a lot of these, and that can tell me X, right? And that's, of course, more expensive because it means somebody has to count them, right? You have to put them under a microscope and you have to count them and extrapolate from the count that you do to figure out what it's probably going to be. So now, how long do your white blood cells last? They are martyrs for your system. When you are really healthy, they live a few days, but during an infection, they give their life every few hours, and you are constantly making more white blood cells. They don't last very long. Okay, so now we're just going to sort of do a tour of like the structure and function of each of the white blood cells and sort of get an appreciation for what each one is doing for you. First thing is there are granular leukocytes that are sometimes called granulocytes. And then there are agranular leukocytes. And this really is kind of arbitrary because it has to do with when I use a certain staining technique. Do you see really distinct grains? However, if I did a different staining technique, I'd see different grains. But this is what they use. So let's just look at them. Can you see from this picture which ones are going to be granulocytes? Yeah. And then this one are agranular, right? Although, by the way, these do have granules. You just have to use a different staining technique on it. So what these have is little balls, little vacuoles of stuff in them that are unique to their functionality, okay? So you got these three, and then you got those two, okay? Let's talk about the granulocytes. All of the granulocytes, everything but the lymphocytes comes from myeloid stem cells. And they have granules in their cytoplasm that stain different colored. And they have weird looking nuclei. So look at the nuclei for all three of these. Okay? These are super weird looking. I'll describe those in just a second. And these are pretty weird looking. And this one, it's hard to see in this figure, but you can see over here. This one has like a little C-shaped nucleus. So part of how you recognize these would be either the granules, right, or the shape of the nucleus, or both. Does that make sense? So you'll get used to it in just a second. So the first type of granulocyte is the neutrophil, and they are the most abundant of the white blood cells that you have. They're the never and never let monkeys eat bananas. And they make up 50 to 70% of your total white blood cells. And the reason they're called neutrophils is because somebody said, well, their granules compared to the other two look kind of neutral in color. Okay, they've definitely got some little pieces, but they're not all red and they're not all purple. So that's why they're called neutrophils. And as far as the shape of their nucleus, the shape of their nucleus is like a multi-lobed nucleus. So it's got this weird nucleus, really, that has a bunch of little chunks hanging off of it. So these are called, sometimes they say they have a segmented nucleus, so they call them segs. Or polymorphonuclear cells, because their nucleus has multiple shapes. And their primary function is defense, not immunity. They destroy mostly bacteria, and they mostly do it by phagocytosis. So they're not really smart, but if somebody clocks them, they clock them right back. Okay? I don't really ever remember anything specific about their attacker, but they always respond. Okay? So these, a higher percentage of these generally indicates an acute infection. So you've got some kind of infection in the area, you've got a massive acute infection. That's why these are phenomenal to see, if you ever get a chance to do this, stain some pus. It is super gross and super interesting. So if you take pus, this is pus off a brain, which is even cooler. So you take some pus, okay, and then you stain it. So remember, before I show you this picture, that what I'm looking for is something that looks like this, right? And then I take the pus and I look at it. The pus does not look like blood, because what pus is mostly a bunch of neutrophils that have donated their entire selves to whooping up on the pathogens, right? So you're going to have some dead pathogens, and you're going to have a whole bunch of neutrophils. And this is a field of pus. Do you see all of those little multinucleated, weird, well, they're not multinucleated, they have that weird shaped nucleus. That's what pus looks like. So cool, right? You're like, I want to stain some pus. And it unfortunately doesn't look like that unless you stain it. So you have to figure out what kind of stain to use. So that's dead neutrophils and other dead white blood cells. Here's another figure of pus. Same thing. Oh, wait. That's the first one. Oh, no, that one. Okay. Okay, so eosinophils is next. Okay, that's these guys. This is the eat and never let monkeys eat bananas. They're nowhere near as abundant. They're usually only 1 to 4%. And they have huge red granules. That's why they are called EO. EO, erythro, always means red. So those are eosinophils. They have a 2-lobe nucleus that kind of looks like lungs. Do you see that? And here too. Okay. And the function of these is they respond to allergic infections or allergic reactions or parasitic infections. So I really hope that it's an allergic reaction and not a parasitic infection. But for instance, if you have some kind of multicellular parasite and you get it in your system, one of the first ways that they can tell is by doing a CBC. And they're like, oh my God, you probably got some tapeworms. Let's go do a poop sample. So a higher percentage usually indicates either a massive allergic condition or a parasitic worm infestation. Ugh. They are found, does this make sense? In very high numbers just below the wall of the GI tract, because that's where you get exposed to most of your parasites. They say that every person on Earth gets at least 2 parasitic infections throughout their life cycle, but luckily you don't usually know about them, which is good because I'm vaguely disturbed by the process. I used to teach zoology, and zoology is like just the entire tour of like the animal kingdom. Half of the animal kingdom are parasites that are trying to get in your parts. It was like so disturbing teaching like that. I'm like, oh my God, this class is making me paranoid about everything. Just like get it through your feet, get it in your eyeball, get it, oh God, everything's trying to kill you. Okay, basophils are next. And basophils are the least abundant. In a healthy person, they only make up about 0.5 percentage point, and they are really easy to locate because they are really, really darkly staining purple granules in them. Okay, so basophils, large, dark, bluish black or purple granules which contain histamine, which is responsible for dilating your blood vessels, and heparin, which is responsible for blood clotting. So that's what those granules have in them. The nucleus, although it's hard to see sometimes, is S or U shaped. And mast cells and basophils are famous for releasing histamine when they're injured. So these are involved in short-term inflammation and also in allergic responses. Okay, and then the last two are your non-granular leukocytes, these guys down here. Okay, and these guys are easy to see because look how intact their nucleus is. So do you see that they're both relatively enormous nuclei? This one right here, the lymphocyte, fills up almost the entire cytoplasm every single time, and it's nice and round. And then this one is the biggest of all of the cells, and the nucleus is usually like shaped like a little kidney bean, but it's really big. Okay, so types of agranulocytes. Let's talk about monocytes first. The monocytes, those big ones right here, those develop from myeloid stem cells in your red bone marrow, and they're the largest of size, but they're the monkeys, and never let monkeys eat bananas. They're hugely phagocytic. They do phagocytosis. They're like your big brawn, not brain, part of the immune system. And if they migrate out of the bloodstream, they're called macrophages. So they're called monocytes when they're in the bloodstream. They're called macrophages when they migrate out. And some of them wander into other tissues. They can wander into the lungs or into the liver, into the spleen and the lymph nodes. The microglial cells are derived from those, but they're not quite the same, so I won't use those as examples on a test. An increase in the number of monocytes usually indicates a chronic infection, not an acute infection, hence mononucleosis. That's one of the indicators of mononucleosis, is that you have an increase in these monocytes. Okay, and then the last one are the lymphocytes. And lymphocytes are these guys right here. They're the most complicated of the stories. I'll do a short version of describing them to you. Okay, lymphocytes are, of course, the only ones that are formed from lymphoid stem cells. Let's go back here. These three are all lymphocytes, even though this one's called natural killer. It is actually a lymphocyte. And so they make up between 20 and 45% of the white blood cells that exist. They are the let and never let monkeys eat bananas. They have a round nucleus and very little cytoplasm. Most of them do not stay in the bloodstream. Most of them migrate into tissues and the lymphatic system. Okay? Their primary function is, these are the smart parts of your immune system. They are responsible for more immunity and less defense. They do some defense, but they're responsible for more immunity. And specifically what they do is they respond to an infection by producing an antibody. Yeah? So if they meet a new antigen, whether it's a pathogen from like chickenpox or an antigen from a mismatched blood transfusion, what they do is they remember it, okay? And part of their memory is they produce antibodies that then they dump into your bloodstream, which will help protect you for the next exposure, right? Somebody clocked you, you remember exactly what it looks like and exactly which corner the person is going to be on. So they produce, respond to specific antigens and produce specific antibodies. And the other thing that they do is that they actually produce cells that remember, and so you have a faster response the next time. So I'm not going to test you over this part, but I'm going to try to tell it to you so that when you take it in micro or have it in cell, you will have heard it before. So you've got B cells and T cells, also called B lymphocytes and T lymphocytes. T lymphocytes are the generals of your immune system. In addition to doing a direct attack, they also tell the B cells what to do and tell the macrophages and the natural killer cells what to do. So the tragedy of HIV is that HIV takes out the generals of your immune system. And then the rest of your immune system doesn't know what to do. So as your T cell count goes down, the rest of your immune system is kind of hamstrung, right? It doesn't know what to do. And then people don't die of HIV, they die of opportunistic infections and cancers because other parts of the immune system were taken out. So, and of course the tragedy of HIV is that the T cells are the only thing that can protect you from viral infections, and then the virus takes out the T cells, right? And so you reduce your protection and you increase your exposure to all opportunistic infections. The B cells, every single time I get exposed to, for instance, chickenpox as a kid, I make antibodies for chickenpox, but then I also make some B cells that are specific to chickenpox so that the next time I get exposed, I make antibodies faster and I make more B cells. So what happens is I am building my immune system with every exposure, assuming that I'm otherwise healthy, right? So what you can do with vaccinations, let's talk about vaccinations, which it's absolutely bizarre to me that vaccinations have become controversial because people freaking died of polio in my mom's generation. And they don't now because of vaccinations. What a vaccination does is it exposes you to an antigen to wake up your immune system, yeah? So what it does is I can take the antigen, and I can either take a killed organism or I can just take the antigen. And I can inject it into my system, and sometimes even squirt it up my nose. And then you respond to the antigen by activating your B cells and your T cells, and you make antibodies, right? So if I do that with chickenpox, that means that when I get exposed to real chickenpox, I'm less likely to submit to the pathogen, right? Because I've got more of a response to it. So that is all involved in this particular story. And all you are doing with a vaccine, it is not poison. It is actually using what we understand about cellular processes to give protection for future exposures. Now, could you just wait to get exposed to things? You totally can just wait to get exposed to things. However, if you are going to wait to get exposed to things, I really hope that you are not allowed to go to school with my kid. Because I don't want them to get exposed to the things that you are going to bring around, right? Because then you are going to basically be a big disease vector because the rest of the school has been vaccinated. So B cells and T cells do direct attack, B cells do produce antibody proteins. What about natural killer cells? That's the last one that they discovered as far as the lymphocytes go. These ones are really interesting. Whenever you have a U cell that looks weird and it's traveling through the bloodstream, the lymphatic system, weird looking U cell is a cancerous or precancerous cell because they've usually got too many nuclei and their shape is abnormal, right? Then what these cells will go is like, I haven't seen you around here before. You look vaguely familiar, but I don't really trust you, and then they trash it. So they do that with cancerous or precancerous cells. Also, viral infected cells look weird. And so they take out your viral infected cells. So back to HIV, did you guys know that with HIV you get types of cancer that you don't get in other situations, like sarcoma, which is this type of skin-related cancer. And that is because HIV takes out the generals, the T lymphocytes, and then they don't direct the activity of the natural killer cells. So you get opportunistic infections and cancers and all that kind of stuff. Good? Okay. We'll just do disorders of white blood cells and then we'll leave before platelets because you guys are ahead of the other class. I don't know why. Okay, last thing is disorders of white blood cells. So leukemia is just a cancer of the blood, but it really occurs in the bone marrow. And it's uncontrolled production of immature or abnormal, non-functional leukocytes. And although it seems counterintuitive, with leukemia, you have more white blood cells than ever, but your immune system is completely trashed. Because what it's doing is just producing them before they're completely able to do their job. So what they do is they produce them in like this stage, and they are not able to function normally, and then they crowd out the normal ones, and they really can cause like your blood to be too viscous. They can cause lots of problems in that way. So they crowd out normal white blood cells, red blood cells, and platelets. So it depends on whether it's this one or this one, whether you have abnormal all cells or just abnormal lymphocytes. Regardless, they end up taking up too much space in your bloodstream. And so infection can occur due to, death can occur due to overwhelming infection because you've trashed your immune system, or hemorrhaging because you have too few platelets. And then a lot of times you will also have problems with carrying adequate levels of oxygen around, which gives you problems with healing. So I think it's on page 660, close to there. You might see new treatments for leukemia, including cord blood transplants. So they do cord blood transplants now. So we'll stop there and we'll do thrombocytes next time. And then we will we'll finish this, and then we'll start on lymphatic system. But lymphatic system is not going to be on your third test, on your fourth test. Okay. Quiz next time over vessels and blood, as far as we've gotten. Actually, I'll go ahead and tell you that white blood cells won't be on it because I didn't get into them in the last class. So it's just going to be at the first part. Okay.